Hello, in this lecture we answer two questions. In the first question, we find out the area of this rectangle ABCD, and in the second question, we find out the area of this green shape that is inside square ABCD. So let's start with the first question. In the drawing, we have rectangle ABCD. Inside this rectangle, we have this semicircle. In addition, we know that this is line segment AEP, that is equals to 6 units in its length. This is line segment PC, that is equals to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. This is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we'll define the center of this semicircle. This point is point O. We'll define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. And we'll define the point of tendency of this semicircle with side DC of rectangle ABCD. This point is point E. We define the radius of this semicircle as x. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. Is equals to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle, that is equals to x. We join points O and E together by a straight line. Actually, we define, because we have 2 points that are here, we define the point of tendency of tangent DC with this semicircle. This point is point M. And we join points O and M together by a straight line. Point O is the center of this semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle, equals to x. Because of the fact that the radius OM, that is equals to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we get here quadrangle OMCB. Inside this quadrangle OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this four-facing angle, in total the must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this four-facing angle must be equal to 90 degrees in its size. So inside quadrangle OMCB, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be its rectangle flat as square. So we relate to quadrangle MOBC is a rectangle because it has 4 right angles. So quadrangle MCBO is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MCBO, side MO must be equal to the opposite side CB. But MO is x, therefore CB, the opposite side CB, must be also equal to x units in its length. In the next step, we join points E and P together by a straight line. By joining points E and P, we create here peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size, according to rule 7. Therefore, peripheral angle APE that subtends on the diameter AE must be equal to 90 degrees in its size, according to rule 7. So, I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. This is a circle, and chord AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore, according to this rule 7, the size of this peripheral angle ACB must be equal to 90 degrees. We have already implemented rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore, according to rule 7, the side of this peripheral angle APE must be equal to 90 degrees. Okay. In the next step, we define this angle as alpha. And we will focus on the right triangle APE. In this right triangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we'll prove that the big right triangle ABC is similar to this small right triangle APE. So I'll write it down. We prove that the big right triangle APE, the big right triangle ABC is similar to the small right triangle APE. Before that, we know that this is angle A, that is a common angle that belongs to both triangles. It is very easy to see that angle A belongs to this small triangle APE, and angle A also belongs to the big right triangle ABC. So angle A is a common angle that belongs to both triangles. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. So can I know that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle A as it is belongs to the big right triangle ABC, it will be defined as angle CAB. And if we relate to this angle A as it is belongs to triangle PEA, it will be defined as angle PAE. So repeat again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC in triangle ABC, and it is equal to this angle, that is actually angle APE in triangle APE. So I repeat again, angle ABC in triangle ABC equals to angle APE in triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle BCA in triangle ABC, and it is equal to this angle, that is actually angle PEA in triangle APE. So I'll repeat again. We found out that angle BCA in triangle ABC equals to angle PEA in triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the three angles inside this big right triangle ABC are correspondingly equal to all the three angles in this right triangle APE. Therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. So if we found out that the big right triangle ABC is similar, this is the sign of similar, to the small right triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We'll derive the side AP of triangle APE over side AB of triangle ABC is equal to side AE of triangle APE over side AC of triangle ABC. So I repeat again, for the fact that those two triangles are similar to each other, we will derive that side AP of triangle APE over side AB of triangle ABC equals to side AE of triangle APE over side AC of triangle ABC. AP is 6 according to what is given as the question, over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE equals to x plus x, that is 2x. This is actually the diameter of the semicircle. So AE is 2x over AC. AC in total equals to 6 plus 5, that is 11. This equals to 11. So in total we should find out that 6 over AB equals to 2x over 11. Here we will cross multiply this equation, and we get that 6 times 11 is equal to 2x times AB. 6 times 11 is 66, so 66 equals to 2x times AB. Here we divide this equation by 2, and finally we get that 66 over 2 is 33, and 2x over 2 is x. So in total this expression equals to x times AB. Here we divide this equation by x, and we get that AB equals to 33 over x. So we should find out that the length of AB is 33 over x units. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually we know that the area of a rectangle equals to the length of the rectangle times the width. Repeat again. We know that the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The width is AB. The length is AB, and the width is CB. Again, the width is CB. So in total, we have found out that the area of rectangle ABCD equals to AB times CB. AB is 33 over x times CB. CB is x. So in total, we have found out that the area of rectangle ABCD equals to 33 over x times x. So we have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33 square units. And that is the answer to the question. Repeat again, we should find out that the area of this rectangle ABCD is equal to 33 square units. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing we have square ABCD. We know that line segment BP equals to line segment PC. And also we know that the area of this triangle PCO is 5 square units. Again, our mission is to find out the area of this green shape. So we define the length of line segment BP as A. And because of the fact that BP equals to PC, PC must be also equal to A. So in total, the length of side BC of of square ABCD is 2a. Therefore, AD must be also equal to 2a, because we know that all the sides of a square are equal to each other. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to side BC. Those two angles are defined as alternating angles, and they are located between the parallels AD and BC. That is to say, AD is parallel to BC. Therefore, according to Rule 15, we have that says that alternating angles between parallels are equal to each other. So those two angles are equal to each other. If we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallels AD and BC. And therefore, they are equal to each other according to Rule 15. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. So in total, we actually found out that all the angles inside the big triangle AOD are correspondingly equal to all the angles of this small triangle POC. We have theta on both triangles, we have angle alpha in both triangles, and we have angle beta in both triangles. Therefore, those two triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big triangle AOD is similar, this is the sign of similar, to the small triangle COP, according to angle similarity rule. So in the next step, I will present to you a new rule that talks about two triangles that are similar to each other, and we will implement the new rule in our drawings. The new rule is Rule 22. According to Rule 22, the ratio of the area of similar triangles is equal to the ratio of the square of the ratio of their corresponding sides. Again, the ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Okay, so in the drawing we have those two triangles that are similar to each other, and according to this rule, Rule 22, the ratio between the areas of those two similar triangles, that is to say, the area of triangle ABC over the area of triangle DEF is equal to the square of the ratio of their corresponding sides. In those two similar triangles, side AC is the corresponding side of side DE, side AB is the corresponding side of side DE, and side CB is the corresponding side of side EF. So the ratio between the areas of those two triangles is the area of triangle ABC over the area of this triangle EDF. And the ratio is equal to the square of the ratio of their corresponding sides. Side AC is the corresponding side of side DE, so it is AC over DE squared. Likewise, the same ratio of the areas of, that is the ratio of the areas of those two triangles, this is actually the area of triangle ABC over triangle EDF. This ratio is equal to the ratio between the square of the ratio of their corresponding sides. Here side AB is the corresponding side of side DEF, therefore it is AB over DF squared. And finally, side CB is the corresponding side of side EF, and therefore it is CB over EF squared. Okay, so in total we found out that the ratio between the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. So we can definitely implement rule 22 in our drawing. Why? Because in our drawing we have already found out that triangle, the big triangle ADO is similar to the small triangle COP. So the area of triangle ADO over the area of triangle OPC, so it is known according to rule 22, because of the fact that those two triangles are similar to each other, we get that the ratio between the areas of those two similar triangles, it is actually triangle, the area of triangle ADO over the area of triangle COP. That is the ratio between the areas of those two triangles. That ratio is equal to the square of the ratio of their corresponding sides. Here, side AD or triangle ADO is the corresponding side of side PC. Therefore, it is AD over PC squared. AD over PC squared. So this equation is the implementation of rule 22 in our drawing. Okay, again, the ratio between the areas of the two similar triangles is the area of triangle ADO over the area of triangle COP. And it is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC, and the ratio between the sides is AD over PC. The square of the ratio is AD over PC squared. Okay? So, the area of triangle ADO is unknown, so we leave it as it is. The area of triangle ADO over the area of triangle COP. It is given as the question that the area of the small triangle COP is equal to 5 square units. Therefore, we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A over PC. PC is A squared. We have A the numerator and A the denominator, so A will get cancelled and we left only with 2 squared. 2 squared is of course 4. So in total we shall find out that the area of the big triangle ADO over 5 is equals to 4. Here we will multiply this equation by 5, and we get that the area of the big triangle ADO is equal to 4 times 5, that is 20 square units. So we actually found out that the area of this big triangle AOD is equal to 20 square units. So because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle OPC. So I write it down. Side AD of triangle ADO over side PC of triangle OPC is equal to side AO of triangle AOD over side OC of triangle POC. So now if you found out that AD over PC equals to AO over OC. AD is equal to 2A over PC. PC equals to A. And it is equal to AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled and we're left only with 2. So if you found out that 2 equals to AO over OC here, we will multiply this equation by OC and we get that 2 times OC equals to AO. If we define the length of line segment OC as B, so we substitute OC by B in this equation. So it is 2 times OC, that is B, is equal to AO. So if we found out that if we define OC as B, then AO is 2B. That is to say, AO is twice as longer as OC. So OC equals to OB and AO equals to 2. OC equals to B and AO equals to 2B. So write it down. If the length of OC is B, then the length of AO is 2B. In the next step, I present to you a new rule and we will implement the new rule in our drawing. The new rule is rule 23. Rule 23 is true in any triangle. So this is triangle ABC that could be any triangle. So here we have a triangle ABC, we have the red line segment AP that divides triangle ABC into two smaller triangles. The first triangle is APB and the second triangle is triangle APC. So line segment AP divides triangle ABC into two smaller triangles, triangle ABP and triangle APC. And according to this rule, rule 23, the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. The area of this triangle ABP is equal to the base, that is BP, times the height, that is H, over 2. And again, the ratio of this triangle ABP is equal to the base BP times the height, that is H, over 2. Likewise, the area of this triangle APC is equal to the base PC times the height, that is H. Both triangles have the same height, H, divided by 2. So the ratio between the area of triangle ABP over the area of triangle APC, here we have triangle ABP over triangle APC. So the area of triangle ABP is BP times H over 2, and the area of triangle APC is CP times H over 2. So the ratio between the areas of those two triangles is BP times H over 2 over CP times H over 2. So we have both in the numerator and the denominator of this expression 1/2, so 1/2 will get cancelled. We have H in the numerator and H in the denominator, so H also will get cancelled, and we are left only with BP times CP. Again, somebody mentioned before, the ratio between the areas of the two smaller triangles is equal to the ratio between their corresponding bases. So the ratio of the area of triangle ABP over the area of triangle APC is equal to the ratio between their bases. The base of this triangle ABP is BP, and the base of this triangle APC is PC. So it is, and the ratio between the bases is BP over CP. So the ratio between the areas of the small triangles is equal to the ratio between their bases. So we can actually implement all 23 in our drawing. Why? Because in our drawing, this is the big right triangle ADC, and this big right triangle ADC is divided into two parts by line segment DO. So all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. According to Rule 23, the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. So I write it down. According to Rule 23, this is triangle ADC. They're divided into two smaller triangles by line segment DO. So the ratio between the areas of those two smaller triangles is the area of triangle ADO the area of triangle ADO over the area of this triangle DOC. So the ratio between the areas of those smaller triangles is equal to the ratio between their corresponding bases. The base of this triangle AOD is AO. So it is AO over OC. OC is the base of this small triangle OCD. So this equation is the implementation of Rule 23 in our drawing. Repeat again, the ratio between the areas of the smaller triangles that created by drawing this line segment DO, we created those two smaller triangles. The ratio between the areas of those two smaller triangles, it is actually the area of triangle ADO over the area of triangle DOC. The area of triangle ADO over the area of triangle DOC. The ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO. The base of this triangle COD is CO. So it is AO over CO. AO over OC. AO over OC is the ratio between the bases of those two triangles ADO and DOC. The area of triangle AOD is 20 square units over the area of triangle DOC. The area of triangle DOC is unknown, so we leave it as it is. and it is equal to AD. AD is 2A over OC. OC is A. So we have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2. So in total, we shall find out that 20 over the area of the small triangle DOC is equal to 2. So here we multiply this equation by the area of triangle DOC, and we get that 20 equals to 2 times the area of triangle DOC. Here we will divide this equation by 2, and we get that the area of triangle DOC is equal to 20 over 2, that is 10. So the area of the small triangle DOC is equal to 10 square units. The area of this triangle DOC is equal to 10 square units. Triangle, the big triangle ABC can go into this triangle ADC according to side rule. Triangle, the right triangle ABC can go into the right triangle ADC. This is the side can go in. It can go into the right triangle ADC. According to side rule. So I'll explain here why the right triangle ABC is going to go into the right triangle ADC. We know that all the sides of square ABCD are equal to each other. So actually, side AB of triangle ABC is equal to side DC of the right triangle ADC. Because it is a square, those two sides are equal to each other. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC, according to the same rule that ABCD is a square. And finally, side AC is a common side that belongs to both triangles, so we can write down that side AC equals to itself is a common side that belongs to both triangles. So in total, we shall find out that the area of triangle ABC can go into triangle ADC according to side rule. We have 3 sides of triangle ABC that are correspondingly equal to 3 sides of this triangle ADC. And therefore those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. That is to say, we will derive that the area of triangle ABC is equal to the area of the right triangle ADC. Why? Because whenever you have two triangles that can go into each other, they must have also the same areas. So the area of triangle ABC is equal to the area of triangle ADC. But we know that the area of this triangle, right triangle ADC, in total it is equal to 20 plus 10, that is 30. So the area of triangle ADC is 30. area of triangle ADC is 30 square units. And we know that triangle ABC, the area of triangle ABC is equal to the area of triangle ADC because they can go into each other. Therefore, they have also the same areas. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We derive that the area of triangle ABC is also equal to 30 square units. So we can find out that the area of this triangle ABC is equal to 30 square units. We define the area of this green shape as x is equal to x square units in its size. So in total, the area of triangle ABC equals to x plus 5 square units. The area of this triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. Here we subtract 5 from this equation and we get that x equals to 30 minus 5 is 25. So in total, we can find out the area of this green shape is equal to 25 square meters. So write it down. We can find out the area of the green shape is equal to 25 square meters. And that is the answer to the second question. So in the next step, I will summarize the lecture. We start with the first question, of course. In this first question, our mission is to find out the area of this rectangle ABCD. So in the drawing, we have rectangle ABC. Inside this rectangle ABCD, we have rectangle ABCD. So inside this rectangle ABCD, we have this semicircle. In addition, we know that this is line segment AB that is equal to 6 units in itself. This is line segment PC that is equal to 5 units in itself. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD are right angles. We define the center of this semicircle. This point is point O. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. And finally, we define the point of tendency of tangent DC in this semicircle. This point is point M. We define the radius of this semicircle as x. Then, so point O is the center of the semicircle, point A is the point on the semicircle itself, so therefore OA is the radius of this semicircle, that is equal to x. Likewise, OE is also equal to x, it is the radius of the semicircle. We join points O and M together by side line. OM is also the radius of this semicircle, that is equal to x. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we get that there, quadrangle MCBO. Inside this quadrangle MCBO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th angle, in total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4th angle must be equal to 90 degrees in its size. So inside quadrangle MCBO we have 4 rectangles. According to rule 5, any quadrangle that has 4 rectangles must be this rectangle not a square. So we relate to this quadrangle MCBO is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle MCBO, side MO must be equal to the opposite side CB. But MO is x, therefore the opposite side CB must also equal to x units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we created peripheral angle APE. This is peripheral angle APE. Let's subtend on AE. That is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle APE that subtends on the diameter AE must be equal to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha and focus on this small right triangle APE. This right triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this trapezium angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this trapezium angle must be equal to 90 degrees minus alpha according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So we can see that angle alpha is a common angle that belongs to both angles. It belongs to the big right triangle ABC, and it also belongs to this small triangle APE. So angle A is a common angle that belongs to both triangles. In the next step, we prove that the big right triangle ABC is similar to this small right triangle APE. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles, so we can write down that angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, in total, we prove that all the angles of this right big triangle ABC are correspondingly equal to all the angles of this right small triangle APE. And therefore, those two right triangles are similar to each other according to angle similarity rule. The big triangle ABC is similar to the small right triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of triangle APE over side AB of triangle ABC is equal to side AE of triangle APE over side AC of triangle ABC. But again, we will derive that side AP of triangle APE over side AB of triangle ABC is equal to side AE of triangle APE over side AC of triangle ABC. AP is 6, according to what is given in the question, over AB. AB is the missing side, so we will leave it as it is, and it is equal to AE. AE is the diameter of the semicircle, that is 2x, over AC. AC in total equals to 6 plus 5, that is 11. So in total, we found out that 6 over AB equals to 2x over 11. Here, because multiplied this equation, and finally found out that 6 times 11 equals to 2x times AB. 6 times 11 is 66. So 66 equals to 2x times AB. Here we divided this equation by 2 and found out that 66 over 2 is 33. So 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. This is AB equals to 33 over x. Again, our mission is to find out the area of this rectangle ABCD. we have to find out the area of rectangle ABCD. We have to find out the area of rectangle ABCD. We know that the area of any rectangle equals to the length of the rectangle times the width. Again, the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of this rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length of rectangle ABCD is AB and the width is CB. So total, we can find out the area of rectangle ABCD equals to the length AB times the width CB. So it is AB times CB. But AB is 33 over x. CB is x. So total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled and we left only with 33. So in total, if we found out the area of this rectangle ABCD is equal to 33 square units. So we finished with the first question. In the next step, I present to you the second question. Actually, I present to you the second question and then we solve the second question of this lecture. Our mission in this second question is to find out the area of this grand shape. So in the drawing we have square ABCD. In addition, we know that line segment BP equals to line segment PC. And the area of this triangle POC is equal to 5 square units. Again, our mission is to find out the area of this grand shape. Okay. First of all, we define this line segment BP as A. And because of the fact that BP equals to PC, if BP equals to A, then PC must be also equal to A. And you also know that all the sides of a square are equal to each other. BC is A plus A, that is 2A. Therefore, AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this is angle theta, then this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to side BC. Those two angles are defined as alternating angles and are located between the parallel lines AD and BC. That is to say, AD is parallel to BC. And therefore, those two angles must be equal to each other according to Rule 15. Rule 15 says that alternating angles between parallel lines are equal to each other. So those two angles are equal to each other. So if this is angle alpha, then this angle must be also equal to alpha because they are equal to each other according to Rule 15. Likewise, those two angles are defined also as alternating angles and are located between the same parallel lines AD and BC. That is to say, AD is parallel to BC. And therefore, those two angles must be equal to each other according to Rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to Rule 15. Okay, so in total, we have found out that the big triangle AOD is similar to the small triangle POC according to angle similarity rule. In both triangles we have alpha, in both triangles we have angle theta, and in both triangles we have angle beta. Therefore, those two triangles are similar to each other according to angle similarity rule. Repeat again. Triangle AOD, the big triangle AOD is similar to the small triangle COP according to angle similarity rule. In the next step, I presented to you Rule 22 and we implemented Rule 22 in our drawing. Okay. So, according to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their sides. So, in the drawing, we have those two triangles that are similar to each other. That is to say, this triangle ABC is similar to this triangle DEF. And according to this Rule 22, the ratio between the areas of those two triangles is equal to the square of the ratio between their corresponding sides. So it is the area of triangle ABC over the area of triangle EDF. That is the ratio between the areas of those two triangles, and it is equal to the square of the ratio between their corresponding sides. In those two similar triangles, side AC is similar to side DE. So it is AC over DE squared. Likewise, side AB is the corresponding side of side DE. So it is AB over DE squared. And finally, in those two similar triangles, side CB is the corresponding side of side EF. So it is CB over EF squared. Okay, and again that according to this rule 22, the ratio between the areas of those two similar triangles is equal to the square of the ratio between their corresponding sides. So I can implement rule 22 in our drawing because we have already found out that those two triangles, that is to say triangle ADO and this small triangle COP, are similar to each other according to angle similarity rule. Therefore, we can definitely implement rule 22 in our drawing. According to rule 22, the ratio between the areas of those two similar triangles is equal to the square of the ratio between their corresponding sides. So it is, what is the ratio between the areas of those two similar triangles? Actually, the area of the big triangle ADO over the area of the small triangle COP. That ratio between the areas of those two similar triangles is equal to the square of the ratio between their corresponding sides. In those two similar triangles, side AD is the corresponding side of side BC. And the ratio between the corresponding sides is AD over PC squared. Side AD is the corresponding side of side PC. The ratio between AD and PC is AD over PC squared. So in total, the ratio between the areas of those two similar triangles is the area of triangle ADO over the area of triangle COP, and it is equal to the square of the ratio between their corresponding sides. That is to say, it is AD over PC squared. So this equation is the implementation of rule 22 in our drawing. So the area of triangle ADO is unknown, so we leave it as it is, or the area of triangle, the small triangle COP. It is given as a question that the area of this small triangle COP is 5 square units. So we substitute the area of triangle COP by 5, and it is equal to AD over PC. AD is 2A and PC is A. So it is 2A over A. We have A in the denominator and A in the denominator, so A will get cancelled. A will get cancelled. So in total we left only with 2 squared, that is 4. So we shall find out the area of triangle ADO over 5 equals to 4. Here we multiply this equation by 5 and finally found out the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. Repeat again, the area of this big triangle ADO is equal to 20 square units. And because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of this triangle ADO over side PC of this small triangle POC is equal to side AO of this big triangle ADO over side OC of this small triangle POC. Repeat again. Side AD of the big triangle ADO over side PC of the small triangle PCO is equal to side AO of the big right triangle ADO over side OC of the small right triangle OCP. AD is 2A and PC is A. So it is 2A over A. This equals to AO over OC. We have A in the denominator and A in the denominator, so A will get cancelled, and we left only with 2 equals to AO over OC. Here we multiply this equation by OC and finally found out that 2 times OC equals to AO. So we define the length of side OC as B, and we substitute OC by B, and found out that OA equals to 2B. So if OC equals to B, OA equals to 2B. That is to say, OA is twice as long as OC. So if OC equals to B, then OA equals to 2B. Okay, so in the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is actually rule 23. According rule 23 is true in any triangle, so this is triangle ABC that could be in a triangle. This triangle ABC, we draw the red line segment AP. By drawing the red line segment AP, we divide the triangle ABC into two parts, into two smaller triangles. And according to this rule, rule 23, the ratio between the areas of those two small triangles that created by line segment AP is equal to the ratio between their corresponding bases. So the area of this triangle ABP is equal to the base of the triangle that is BP times the height that is H over 2. So again, the area of triangle ABP is equal to the base BP times the height H over 2. The area of this triangle APC is equal to the base PC times the height that is H, because both triangles have the same height that is H over 2. So the area of triangle APC equals to the base PC times the height H over 2. And the ratio between the areas of those two triangles is actually BP times H over 2 over CP times H over 2. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have H in the numerator and H in the denominator, so H also will get cancelled, and we'll have to live with BP over CP. That is to say, from this equation we can conclude that the area of those two smaller triangles that created by line segment AP is equal to the area of their corresponding bases. That is to say, the area of this triangle ABP over the area of this triangle APC, that is the ratio of the areas of those two triangles, is equal to the ratio between their corresponding bases. That is to say, it is the base BP of triangle ABP over the base PC of triangle APC. So it is BP over PC. Repeat again that the ratio between the areas of the two triangles that were created by line segment AP is equal to the ratio between their bases. So we can actually implement rule 23 in our drawing. Why? Because in our drawing, this is triangle ADC, the right triangle ADC, and the right triangle ADC has been divided into two parts by line segment DO. It's divided into two smaller triangles. The first small triangle is ADO, and the second small triangle is triangle ODC. And according to rule, so actually all the requirements of rule 23 are satisfied, and therefore we can implement here rule 23. According to rule 23, the ratio between the areas of those two small triangles that they were created by line segment DO, the ratio between the areas of those two small triangles is equal to the ratio between their bases. So that is to say, the ratio between the areas of those two triangles is actually the area of triangle ADO over the area of triangle DOC, and it is equal to the ratio between their bases. The base of triangle AOD is AO, and the base of triangle DOC is OC. So it is AO over OC. AO is actually AO over OC. Repeat again, the ratio between the areas of those two smaller triangles is equal to the ratio between their bases. The base of triangle AOD is AO, and the base of triangle DOC is OC. So the area of triangle ADO is 20 square units. Over there, target DOC. There, target DOC is unknown, so we leave it as it is. So it is equals to the base of this target ADO, that is AO, it is 2B. Here it is actually 2B over CO. CO is B. Repeat again. AO equals to 2B and CO equals to B. So it is 2B over B. So 20 over there of the small target DOC equals to 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, if we found out the 20 over there of target DOC is equal to 2. Here we multiplied this equation by the area of target DOC, and finally found out that 20 times the area, 20 equals to 2 times the area of target DOC. Here we divided this equation by 2 and finally found out that the area of target DOC equals to 20 over 2, that is 10. So in total, if we found out that the area of this small target DOC is equal to 10 square units. It is very easy to see from the drawing that triangle ABC can go into triangle ADC according to side rule. Because of the fact that ABCD is a square, all of its sides are equal to each other. So it is very easy to see that the right triangle ABC can go into the right triangle ADC. Why they can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC because it is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC. Because of the same reason, because ABCD is a square. And finally, side AC is a common side that belongs to both triangles, so we can write down that AC equals to itself is a common angle that belongs to both triangles. So in total, if we found out that the area of triangle ABC, the triangle ABC can go into triangle ADC according to side rule. Okay? And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of this triangle ABC is equal to the area of this triangle ADC. And again, note that the area of triangle ABC can go into triangle ADC according to side rule. And from the fact that they can go into each other, they must have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. But we know that the area of triangle ADC is 20 plus 10, that is 30. Repeat again. From the drawings, it's very easy to see that the area of triangle ADC in total is equal to 30 square units, and we already found out that the area of triangle ABC is equal to the area of triangle ADC. And from this equation, the area of triangle ABC is equal to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square. The area of triangle ABC is equal to 30 square units from one side. But from the other side, if we define the area of the green shape as x square units, that is to say, the area of the green shape is equal to x square units according to our definition, then the area of triangle ABC in total will be equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to, the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and finally found out that x, that is the area of this green shape according to our definition, is equal to 25 square units. And repeat again, we found out actually that the area of this green shape is equal to 25 square units. Okay, thank you very much.